Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This is the second half of a lecture on solving medium-sized systems of linear equations. By medium, I mean 3 by 3 systems. We just finished our talk on what a 3 by 3 system is, as well as how to solve 3 by 3 systems, and now we're going to focus on applications. Prior to solving any type of application, I do want to cover again, like I have in the past, Poya's problem solving method, which essentially is just a method on how to tackle any type of word problem or application. And some of this is pretty obvious. Like the first step to obviously problem solving is to read the problem. If you don't do that, you can't go anywhere. The next step is to really understand what's going on. Sometimes that involves drawing a picture. The next step, which is often underused, is labeling the unknowns. That's extremely important because often you'll get students who label unknowns incorrectly, or they might just start labeling within the middle of a problem. They lose what their variables are. So it's important at the beginning to use words like let x equal or whatever variable you're using. By the way, you don't have to use x, y, and z. You can use any letter that you think should represent the situation. The next step is actually the hardest step for most students, is to build equations involving these unknowns. It is pretty much the most difficult step in the problem solving process, and there really is no hint that I can give to building equations properly, other than to know your formulas and to think logically about a situation. Finally, once you build your equations, you'll probably have a system of equations. You can solve that system and then check your solution. Now, I have to apologize. This example, and in fact several of these examples, are from an older textbook, and so I haven't updated the prices on them at all. As you're about to see, a coffee company is going to blend 3 coffees. You have 3 different types of coffees: a Colombian, a Kenyan, and a Peruvian, and they're worth $1.20 a pound, $2 a pound, and $1 a pound, respectively, which obviously does not represent today's prices. The final blend, after you mix these things up, is going to weigh about 5,000 pounds and cost $1.66 a pound. So you're going to mix these in, or mix these up to get 5,000 pounds of coffee blend, that is, and you want that cost to be $1.66 a pound. There also must be about twice as much of the Kenyan coffee as the Colombian coffee. So how much do we need of each type of coffee? Well, the first thing I did is I read it. So read it. I understand what's going on. I'm going to be blending coffee. So the next thing to do is label my unknowns. So I am going to, and maybe I'll do this in blue so that you see I'm actually starting the problem. I'm going to go ahead and say let C equal the amount of Colombian coffee, and I'll do the same for K and for P for the Kenyan and Peruvian. The reason why I chose these variables, or actually why I'm looking for these amounts, is because this last sentence, this question here, how much do we need of each? That's an indication to me of what we're looking for, really. How much of each coffee are we going to blend? So those will be what I'm going to use for my variables. Now, the next part is actually the hardest part, and actually let me go ahead and indicate on here that I've now labeled the unknowns. Actually, let me do this. So I labeled, I understand I read. So the next thing is we need to build equations. And like I said, that's usually the most difficult part for students. And how I'm going to do this is kind of a mixture of different tactics. One thing is, if I ever do a mixture problem, which means that you're mixing in one ingredient with another ingredient, that type of thing, I usually draw a picture. And the picture I draw is vats of objects. So I have a vat of Colombian coffee, and to that I'm going to add a vat of Kenyan coffee, and to that I'm going to add a vat of Peruvian coffee. And then in the end, when I mix all three of those vats together, I should get a final vat of a mix. Okay, so this will be my mix. And what I'm going to do, so this would be, well, I'll label these in a moment. Just like if you go to a store, you normally in a store see like a price tag on each of these objects. Well, there happens to be prices for each of these here. For example, the Colombian is at $1.20 per pound. So I'll write the per pound like that. And that's for the Colombian. And the Kenyan is $2 per pound. And finally, the Peruvian is $1 per pound again. And the mix we want to sell for $1.66 per pound. It's just like you would notice in a store. These have price tags on them. Also, when you notice, what you'll notice in the store is how much each of these weigh. They usually say at the bottom how much they weigh. And since I don't have room here at the bottom to write in on the bag how much they weigh, I'll write it below. We don't know how much this vat weighs, but we do have a letter for it. C is the amount of Colombian coffee we have, so C is what we're going to call that, because C is the weight of it. And following the same suit, K will be the weight of the Kenyan coffee, and P will be the weight of the Peruvian. Altogether, we need 5,000 pounds, so the mix is going to be 5,000. And these, by the way, each of these letters are the amounts in pounds. All right. If you look at this, there's actually two equations staring at me right now. And I could show you this. Actually, I think I will. There's one equation that just relates kind of how much coffee we have. I know the amount of Colombian, the weight of this bag plus the weight of the next bag plus the weight of the third bag should equal 5,000 pounds. So I know that C plus K plus P should equal 5,000. And then we also have something that is pretty easy to grab from this. I know that how much I'm going to spend on this Colombian coffee. If it's $1.20 a pound and I buy C pounds of it, it's going to be $1.20 times C. For example, if I bought 10 pounds, it'd be $1.20 times 10, or $12. So I know that I'll have this, $1.20 times C plus the amount of money I'm going to spend on the Kenyan coffee, which is $2 times K, plus the amount I'm going to spend on the Peruvian coffee, which is pretty easy because it's just $1 per pound, so $1 times P. And then finally, that should equal the amount that I would spend on the mix. If it doesn't, then you're overspending for your coffee or underspending for your coffee. So this should end up being $1.66 times the 5,000 pounds. That's the total cost. Now, if you notice what I'm doing here, I'm basically grabbing this price and multiplying it by the pounds, and this price and multiplying it by the pounds, and this price multiplying it by the pounds, and again, this price and multiplying it by the pounds. So I get two equations thus far. Now I need one more, right? Because we have three unknowns, you need three equations. Well, they give us the last sentence here. There must be twice as much Kenyan coffee as Colombian coffee. So let me present you with two possibilities. There must be twice as much Kenyan as Colombian, or is it going to be K equals 2C? This is a common mistake. One of these is absolutely wrong, one is right. The best way to determine which one is right, if you ever have problems like this, and most students do, is to try a value. In other words, I know there's going to be twice as much Kenyan as Colombian. So if I have 1 pound of Colombian, right, I should have 2 pounds of Kenyan, because there's twice as much Kenyan as Colombian. So let's see. Substitute those values, 1 and 2, in for the letters here. If C is 1 here, and K is 2, is it true that 2 times 2 is equal to 1? Heck no. That doesn't work out. Check it over here though. If C is 1 and K is 2 equal to 2 times 1? Yep. So that's our third equation right there, k equals 2c. And now we're going to go ahead and solve this system. Once I get to where I have three equations with three unknowns, I can then forget about the word problem for a little bit and spend my time solving it. So let me put a check mark under the equations. We're just going to go to solving now. So I bring us to a new page here so that I can kind of do my work up here. First thing I'll probably do is write these in standard format. So in other words, I'll rewrite, I have a c plus k plus p is equal to 5,000. The second equation, I will clean up a little bit. You could either multiply both sides by 100 to get rid of the decimal, or you could leave that 1.2 there. Actually, you don't have to multiply by 100. You can multiply by 10. And in fact, I think I will. I'll multiply both sides by 10, so I get 12c plus 20k plus 10p is equal to, this product right here is 8,300, so if I multiply that by 10, it's 83,000. Finally, downstairs here, I'm just going to subtract 2c from both sides. Get that business. So here's our system of equations. I'll call this row 1, row 2, row 3. Again, I've forgotten about the word problem at this point because now I'm just in the process of solving a system of equations. And I need to pick a variable to kill off. Well, if I look at this system right now, I have one equation that's already missing a value for p. So what if I were to grab row 1 and row 2 and kill off p? Then I would have an equation without p already and another equation without p. So that would be a good choice. So what I'm going to do is take a negative 10 and multiply that by row 1, and then I'll add that to row 2. So here let's do negative 10 times row 1, which is going to be a negative 10c minus 10k minus 10p equals, and remember to multiply both sides, so a negative 50,000. And then row 2 is just 12c plus 20k plus 10p. And that's equal to 83,000. If you add these up, you get this beautiful 2c plus 10k is equal to, let's see, it's 33,000. So now I have an equation involving only c's and k's, and I have another equation right here that involves only c's and k's. So now I'm ready to group those two together and start a whole new system of equations here. And this whole new system is going to be very easy for us to solve because it actually has this beautiful property where I could just add them up and the c's will cancel. I'll get 11k is equal to 33,000. And that's actually pretty quick to solve because I know 11 goes into 33 3 times. So 11 goes into 33,000 3,000 times. So k is 33,000. Or 3,000, I'm sorry, not 33,000. K is 3,000. Let me go ahead and write that over here so that I have this kind of nice and clean, ready to go. Now that I know that what k is, I can substitute that back into either of these two equations, either this one or this one, the ones that only have k's and c's. And it looks like the second one would be the easier one to substitute into. So I'll go ahead and say, okay, that means that negative 2c plus 3,000 must equal to 0. Subtract 3,000 from both sides. And divide both sides by negative 2. That should be 1,500, I guess. So c will equal 1,500. And then finally, I need to know how many pounds of the Peruvian, and there's a lot of ways you can think about this. One is just to use logic. The fact is I need 5,000 pounds altogether, and I already have taken up 4,500 of it. So the amount of Peruvian should be 500 pounds. Another way you could do it is just go back to any of the original equations, specifically this one since it's the easiest, and just plug in 1,500 for C, 3,000 for K, and find out what P is. And when you do that, you'll get that P is equal to 500. Finally, in the end, when you're done solving an applied problem like this, you should always state your solution. I'm just going to state it out loud that you need 1,500 pounds of Colombian coffee, 3,000 pounds of Kenyan coffee, and 500 pounds of Peruvian coffee in order for you to make a mix that weighs 5,000 pounds, that costs $1.66 per pound, where the amount of Kenyan coffee is twice the amount of Colombian coffee. Let's try something a little bit different. It's kind of an odd systems problem here, but still a fun one, I think. A 3-digit natural number is such that the sum of the digits is 6. If the digits are reversed, the resulting number is 99 larger than the original number. Also, the tens digit is equal to the sum of the ones and the hundreds digit. Find the original number. So I've read the problem. It's right over here. I've read it. I understand what's going on, even though I may not know how to solve it immediately, but it's still a pretty cool problem. I understand that we got a 3-digit number. I'm going to probably have to reverse it at some point. I know the sum of the digits right now is 6. I know that when I reverse it, it's 99 digits or 99 larger than the original number, and I also know that the tens digit is equal to the sum of the ones and the hundreds. I know that stuff. So we have to label some unknowns, and the things we don't know are the digits themselves. So we'll go ahead and let's see. I don't want to do like ones, tens, and hundreds. The reason why is because 1. If I use O for 1, it looks like a 0. So I'm just going to let X equal the hundreds digit and Y equal the tens digit, and so on and so forth. So I know I have a number that looks like this, X, Y, Z. Okay, that's my number. So now let's use these variables to figure out this problem. Let's see. 3-digit natural number such that the sum of the digits is 6. Okay, so that means that X plus Y plus Z is equal to 6. That's our first equation. Not bad. That was pretty quick. If the digits are reversed, the resulting number is 99 larger than the original number. So here's where it's going to get kind of tricky. Because if you look at this number right here, XYZ, if you look at that number, it's going to look to you like it's X times Y times Z. These are not multiplications. Really, if you look at a number like, let's say 831, that's really saying I have 8 times 100 plus 3 times 10 plus 1 times 1. I have the hundreds digit, the tens digit, and the ones digit. So that's how this number is structured. I have 8 sets of hundreds, 3 sets of tens, and 1 set of ones. So this number XYZ is actually 100 X times 100 plus 10 times Y plus 1 times Z. That's actually the lengthy version of that number. Unfortunately, I shouldn't have that number written there. You'll start to think that's part of this system. So I'll move it right up to the upper right hand corner. So if you have a 3-digit number, you can break it into the hundreds, the tens, and the ones. So this second sentence, if the digits are reversed, the resulting number, this reversed number, is 99 more than the original number. So let's reverse the digits here. So we'll have Z, Y, X. So in other words, we'll have 100Z plus 10Y plus X. That's the reverse order of the original number, XYZ. That is 99 more than the original number. And the original number is going to be 100X plus 10Y plus Z. There's the original number. Here's the reverse number. The reverse number is just 99 more than that original. So there's another equation right there. Finally, the tens digit, which is Y, is the sum of the ones digit and the hundreds digit. The hundreds digit and the ones digit. That happens to be three equations with three unknowns. And at this point, I'm just going to only worry about cleaning this up really quickly. So the first equation is already clean. It's x plus y plus z is equal to 6. Second equation, I'll move all the variable terms to the left-hand side. So I'll subtract 100x from both sides, so I'll get a negative 99x. I'll subtract 10y from both sides, and that actually disappears. And I'll subtract a z from both sides, so I should have a plus 99z. And this is supposed to equal 99. And then the third equation, I'll move all the variable terms to the left-hand side as well. And I see one other thing that I can do to clean this up. I'm going to divide the middle equation by, let's divide by just regular old 99. So I'm going to take 199 and multiply it by row 2 to become the new row 2. It's just to kind of clean this up. So I'm going to rewrite x plus y plus z is equal to 6. And then I'll have a negative x plus z is equal to 1. Just kind of makes it nice, that's all. And now I'm looking at this and I'm thinking to myself, okay, I would like to probably take advantage of the fact that this middle equation here only has an x and a z. So I'm going to go ahead and take row 1 and row 2 and kill off the y variable, so I have another equation with only x and z. So I go to a new page to do this, but so I'm going to look at a negative row 1 and add it to row 3. Negative row 1 is a negative x minus y minus z is equal to a negative 6. I'm going to add that to row 3, which is a negative x plus y minus z is equal to 0. When I add those up, I'll get a negative 2x. The y's cancel, I'll get a negative 2z is equal to a negative 6. And in fact, I can even divide both sides of this equation by a negative 2 if I wanted to. If I want to do that, that'll just be x plus z is equal to a positive, oops, not 6, but a positive 3, because I divided both sides by a negative 2. Just gets a little cleaner. So I'll go ahead and take this equation right here with x's and z's and the equation up above with x's and z's and glue them together in the final system that I need. Negative x plus z is equal to 1 and x plus z is equal to 3. This I could just straight add them up. The x's will cancel. I'll get 2z is equal to 4. Divide both sides by 2 and I'll get z is equal to 2. So I happen to know the ones digit is going to be 2. I can now plug that z equals 2 into either of these highlighted equations, actually. I'll just plug it into this one. So x plus 2 is equal to 3, or in other words, x is equal to 1. So I know now that the hundreds digit is equal to 1. Now my last step is to plug x equals 1 and z equals 2 into the first equation, or any of the equations, but the first equation is the easiest. So I'll do that. 1 plus y plus 2 is equal to 6. That's 3, so subtract 3 from both sides, you get y is equal to 3. And so I know the number that they're talking about is 132. If I reverse the digits and it becomes 231, that's 99 more than 132. Also, I know that if I add up these digits, it's 6. Also, I know that the tens digit is the sum of the ones digit and the hundreds digit. That's my answer. As a final example, we're going to take something that I often had found to be very challenging when I was a student. These are table style problems. I've never been a very good logic thinker when it comes to tables, so I thought I'd do an example of one here and explain my thought process to solve these. The composition of three types of steel are given below. How many types of each? That's not what it says. How many tons of each type should be melted and mixed together to get 20 tons of a steel that is 72.1% iron, 8% nickel, and 19.9% chromium? So let me get this straight because this is a very important thing to recognize in this problem. What are they asking us to find? I mean, I've read this problem. I think I understand it. We got three different types of steel, and we want to melt them together to get a certain specific, a new kind of steel that has a certain percentage of iron, nickel, and chromium. So I think I understand that. But the most important part of solving a problem like this is to label your unknowns properly. So it's asking us how many tons of each type should be melted and mixed together. That's what they want to know. How many tons of each type? There's three types, type A, B, and C. So I will let A equal number of tons of type A that we use. And you get the idea for the rest of the variables. B is just the number of tons of type B we're going to use, and C will be the number of tons of that type C steel. Okay, so we have three kinds of steel. A will be the number of tons of type A, and so on and so forth down the line. So I know right now, okay, that I should get three equations because I have three unknowns. And my equations should have the variables A, B, and C in them. A, B, and C. A, B, and C. It's just so important for you to set it up like this because if you don't, you could run around in circles for quite some time. Now, if you look at that table, I have a row for type A, a row for type B, and a row for type C. So I guess the rows here correspond to my columns here. So I guess the columns, like the iron column, the nickel column, and the chromium column, must correspond to my rows here. So I have an equation that's all about the amount of iron, and I have an equation that's all about the amount of nickel, and I should have an equation that's all about the amount of chromium. So let's look at the iron equation. What percentage of iron do we want to get in the end? Well, I want to get 72%, 72.1% iron in the end. And remember, this is a percentage, so it's 0.721. And you have to understand that's 72.1% of 20 tons. So that's why I get that 20 there. Now let's look at the amount of iron for type A. 72% of type A will be pure iron. So that's 0.72 of this amount of A will be pure iron. Plus the amount of iron that I get from the type B steel, which is 68% of that is pure iron. Plus, I know 75% of the type C material is pure iron. Okay, let's go to the nickel row here. I know that I want in the mix, I want it to be 8% nickel. So 0.08. And that's of that 20 tons. So I want 8% of that 20 tons to be pure nickel. So let's see. The amount that's contributed from type A, well, 8% of type A is pure nickel. And 11% of type B is pure nickel, and 21% of type, oops, not 21, it's 6% of type C is pure nickel. Okay, finally let's talk about the chromium. I know the amount of pure chromium in the final mix is going to be 19.9% of that 20 tons. And now the chromium from type A is 20% of type A's chromium, and 21% of type B is pure chromium, and finally 19% of type C is pure chromium. So I see I have three equations, three unknowns, and we're ready to go. One thing I probably will do here is multiply all three equations by 100 so that I can get rid of the decimals. So I'll go ahead and do that in one fell swoop. Now, to be honest with you, when I look at this system of equations and start asking myself, like, oh, okay, what variable do I want to kill off? There's nothing that really jumps out at me as a variable I want to kill off in any of these equations. Maybe A. A might be the easiest variable to kill off. So let's go ahead and I'll open up a new page and we'll do that. Now, before I begin into this, I just want to say that it is there is a very nice method for solving systems of equations called Gauss-Jordan reduction or Gaussian elimination. And you would use matrices with that. So if you happen to know matrices, it makes this problem much, much easier. However, that was not the subject of this lecture, so I'm going to go ahead and do this without Gauss-Jordan elimination. To kill off A, I will take negative 9 times row 2. By the way, let me label my rows. Row 1, row 2, row 3. I'm going to take negative 9 times row 2 and add it to row 1. And you'll see that that actually is a good choice here. So negative 9 times row 2 is a negative 72a minus a 99b minus 54c is equal to a negative 1440. And then row 1 is just 72a plus 68b plus 75c is equal to 1442. So I'm going to add these two up. By design, the a's will cancel. We'll have a negative 31b, and what is that? That's a positive, actually. A positive 21c is equal to 2. Okay, so we successfully got rid of the variable a here, and we're just dealing with b's and c's. So now we have to kill off a's using two different rows. I'm going to use row 2 and row 3. I'll have to manipulate both rows, actually. So what I'm going to do is do a negative 5 times row 2, so it'll be a negative 40 on the a there. And then 2 times row 3, so that's a positive 40 on the a there. And I'll add those up. So here we go. Negative 5 times row 2 will give me a negative 40a plus, oh no, minus 55b minus 30c is equal to 500, 800, negative 800. And then twice row 3 is just going to be 40a plus 42b plus 38c equals, that's nearly 800 minus 4 is 796. Okay. And we'll go ahead and add these up. You'll see the a's cancel. Again, by design. The b coefficient will be negative 13, I think. Let me just double check my math there. Yeah, it's negative 13. And this will be a positive 8c, and this will be, let's see, a negative 4. So we have two equations now left over and two unknowns, both involving b's and c's. So I'll group them up. Negative 31b plus 21c is equal to 2, and a negative 13b plus 8c is equal to a negative 4. And I almost have to laugh because this is just tragically horrible as far as these go. You can't get much worse than this. So it happens, and you should be able to see a complicated example. So this is absolutely fine for us to take our time through this one. Let's kill off a variable. The C variable is fine to kill off here. It'd be easiest if you just multiply row, we'll call this again row 1, so I'm relabeling here. We'll multiply row 1 by a negative 8, and we'll multiply row 2 by a 21. And this is just a common tactic, and then we're going to add these up. So let's go ahead and do that. Should be a 248b minus, let's see, 168c is equal to a negative 16. So that's me just multiplying row 1 by a negative 8. Now, multiplying row 2 by 21, I'll get, let's see, a negative 273b. 21, now it's by design, it should turn out that 21 times 8 here is also going to be a positive 168, which it is. And then 21 times a negative 4, it's 21, right? Yeah. 21 times a negative 4 is negative 84. All right, let's see what happens when we add these up. When we add these up, I see that the C's cancel, and the B's, we get a negative, let's see, 25b. And over here, when I add up this stuff, I get a negative 100. Oh, that's a very nice thing. B is equal to 4. Well, I know I must be on the right track if I get a pretty number like that. Now, it's not always true that you're going to get pretty numbers like that, but once I see that b is equal to 4, I know that I have done things correctly. Now that I have that b is equal to 4, I could plug 4 for b into any of my equations only involving b and c, that is. I'm going to choose this one right here because it's a smaller version of the coefficient for b. So I'll have a negative 13 times 4 plus 8c should equal a negative 4. So that's at 40, 52, negative 52 plus 8c is equal to a negative 4. I'll add 52 to both sides, so I get 8c is equal to 52 minus 4 is 48. Divide both sides by 8, I get c is equal to 6. And now that I know what b is and what c is, I can plug those into any of my previous equations, and you better believe I'm going to choose this middle equation here because the coefficients on everything are kind of small. So here I go, 8a plus 11 of those b's, which are 4, plus 6 of those c's, which are 6, should equal 160. That's 8a plus 44 plus 36 should equal 160. 44 plus 36 is 70, 80. Subtract 80 from both sides. I get 8a is equal to 80 actually, so that's a equals to 10. At this point, I don't even remember what the original problem was. So I'm going to have to go back and look. But we know it's 10, 4, and 6 for the variables. Okay, so here's the original problem. Remember, we got a is equal to 10, b is equal to 4, and c is equal to 6. Okay. So what does that mean? If I want to make a steel mix that's 20 tons, such that that steel is made up of 72.1% iron, 8% nickel, and 19.9% chromium, I'm going to mix 10 tons of steel type A with 4 tons of steel type B with 6 tons of steel type C. Notice that A plus B plus C equals 20. So we are completely finished. That was more of a droll example, sorry about that, but very what I consider one of the more challenging styles that you'll see in a 3 by 3 system.